Okay, so welcome to the presentation of the paper Reconstruction of Pairwise Interactions using Energy-Based Models. And in this paper, we look at a situation where we want, for various reasons, to describe the variability in a system using probabilistic modeling, and where we already start with a nice and simple and abstract model that we maybe made by hand, and which already describes a lot of the variability in the system, but from which we also believe that it doesn't really capture all of the complexities. And what we do in this case is to say, okay, we can actually keep our simple model, but we add a black box neural network model to it. And then what we do is to fit both parts, so the simple model and the neural network, together. And then we use this combined fitted model for solving the task that we want to solve, which in our case is the reconstruction of pairwise interactions. So basically determining how strong the links between pairs of variables are. Okay, so for a one-slide summary of the talk and also of the paper, I'm going to talk about knowledge integration, which is the general question on how can I integrate knowledge into a machine learning pipeline. I'm going to talk about energy-based models, which are models where we specify only the negative unnormalized log probability of a state of the system, which is also called the energy. Then I'm going to talk about hybrid EBMs, where the energy is divided into two parts, a part that is relatively simple and interpretable, and a part that is a neural network. And in the end, I'm going to talk about how we can use these kind of models for a specific task, in this case, the reconstruction of couplings or pairwise interactions. Let's start with knowledge integration. Obviously, in the last years, there have been a lot of successes using data-driven black box approaches, the most famous one being deep learning. And there are a lot of people who say that this is the future, so you shouldn't use your limited resources to try and understand the underlying system better. What you should do is to try and get more data and more computational power, and in the long run, you're always going to fare better in that way. However, right now, domain knowledge and modeling are actually still very relevant, and there are a couple of good reasons for that. One is that even if you have large and increasing computational power, you might run into the problem that you just don't have enough data, in which case your computational power and your large models are just not that useful. Then there's also an issue with these black box approaches around interpretability and fairness. And the issue is that in certain fields, like for example in medicine, certain branches of finance and other fields, you often really want to be able to give a very good reason for a decision that you make. And if you base that decision on the outputs of one of these black box approaches, this very often just isn't possible, and that's a problem. And then last but not least, obviously in natural science, we're not only interested in making the best possible prediction, we're also interested and even more interested in understanding the underlying system. And the best way to do that is to actually take what you believe to know about your system, make a model out of it, and then check if your model is any good. And the idea now is that these two fields, these two ideas here, they're not necessarily a dichotomy. So you can leverage both worlds in a hybrid modeling approach where you say, okay, I use my domain knowledge, but I also use the powers of black box approaches. And in that way, I just get the best of the two worlds. And that directly brings us to the problem of knowledge integration. So how can I put the knowledge that I have into a machine learning pipeline? And there are actually a lot of different types of knowledge that I might want to integrate. So for example, I might have really some algebraic equations. So I might be, for example, able to constrain the different outputs of my system by my knowledge, for example, because I have an equation that relates them, or I have some inequality. I might be able to say something about invariances, which obviously is very important, for example, in computer vision. So I know that certain rotations and certain translations shouldn't alter the output of my classifier. I might also have really something like human feedback that I might want to integrate. And the kind of knowledge that is most pertinent to what we want to do in the paper that I describe here are probabilistic relations. So for example, if you already know roughly what kind of distribution you would expect your system to follow, you can think about how you can include this knowledge in your machine learning model. In the paper, we work in the framework of generative modeling, where we are given a dataset D of M samples, and the task is to generate new samples in some sense consistent with the data distribution. And you can often also do more with the inferred models. So for example, you can go back and look at the parameters that you have inferred and then try to interpret them in terms of the underlying system and then learn something about the underlying system. So the system that generated the dataset D. There are a couple of prominent generative model types. Just some of them are the variational autoencoders, generative adversarial networks, autoregressive neural networks, and energy-based models, and they all have different trade-offs. So they might be more or less complex, they might be better or less well-suited in certain applications, and for some of them you might actually be able to calculate the likelihood, and in some of them the calculation of the likelihood is intractable. An important characteristic is compositionality. So if we think of a distribution as a set of constraints, so a constraint on what kind of samples I would expect and what kind of samples I would not expect, what happens if we have several such constraints? Can we combine these sets of constraints easily in these models? And for this, especially well suited are the type of models called energy-based models, which borrow their form directly from statistical mechanics, where I specify the negative log probability in an unnormalized form, which is then called the energy, and this then defines my probability distribution. And these kind of models are well studied. You can train them using a standard maximum likelihood objective, and they have a couple of pros and cons. The pros are that they're relatively simple and flexible, so it's really just this equation here which defines them. And if you want to combine several of them, so several energy-based models, it's really easy to do because you can just add the two energies. So if you have a model E1 and a model E2, you just add them, you get a third energy, which corresponds to multiplying the probabilities here. The cons are that they're relatively hard to train, they're hard to sample from, so you need to use, typically you use Monte Carlo approaches, and that's all connected to the fact that the likelihood is known only up to a normalization factor. So in most cases, this Z here, which is the normalization factor, is just intractable to calculate. A very easy and very popular way of defining the energy, for example, for binary variables, is to say that you want it to consist of two types of terms. One type of term which depends only on one variable, and one type of term which depends on two variables. And the parameters in this part are then called fields, and in this part are called couplings. And those are then pairwise models. And such pairwise models already capture a good part of the distribution in many applications. So for example, you can use them for describing the variability in neuronal spikes, and then you can infer this model and look at the couplings and connect them to effective couplings between neurons. You can also use pairwise models, for example, for protein sequence data, where you again infer the model and then you look at the couplings and connect them to contacts between different parts of the protein. Even though in proteins you don't really have binary data, so the variables don't just take two values, but they can take typically 21 values, but it's a straightforward extension of this model here. And here now you would already expect, because both of them are actually quite complicated biological situations, that in the generating distribution, you also probably have higher order terms, which means that not only you don't capture these higher order terms, but because you have a model mismatch, it might also be that the existence of these higher order terms distorts the inference of these couplings. And that's exactly the kind of problem that we look at in the paper. So we know that in many of these systems, pairwise distributions are already a very good approximation, but we also believe that there are higher order terms. The problem is we don't know what those higher order terms are, and there are exponentially many of them. So one approach now would be to say, okay, let's just forget about pairwise models and use directly a complicated neural network. But that would also mean throwing away this prior knowledge that pairwise models are already a very good approximation. So in the paper, we opt for a different approach and define a hybrid energy that consists of a pairwise energy plus a neural network. So we model this pairwise energy here explicitly, which would be that part here, where we don't add fields, but that would be an easy extension to add if wished. And then we add a energy based on a neural network, where we can actually use any architecture that we like as long as it outputs a real number. And the idea then is that if my underlying distribution is really of that type, where I have a pairwise distribution plus some higher order terms, then we could hope that this part here models the pairwise distribution and the neural network picks up these higher order terms. We test our approach on binary sequences, and because our hybrid models are really just energy-based models, we can use standard techniques for training. In our paper, we use pseudo-likelihoods, where we replace the likelihood of a complete sequence with the likelihood of one position in the sequence given the other positions in the sequence, and the objective functions that you can build out of that is tractable. You can calculate it, and you can train the complete hybrid model then using standard backpropagation techniques. We test the hybrid models on a specific task, namely the reconstruction of couplings, and we do this in a synthetic setting where we define a generating distribution, which is again an energy-based model, which contains a pairwise part plus some higher order interactions where we use n randomly sampled higher order interactions, and we introduce a parameter gamma, which regulates the strength of these higher order interactions versus this pairwise part. And we just generate samples using Monte Carlo methods from this model here, and then we check if we can infer these couplings here. One problem that we still have to solve is how to extract the pairwise interactions from the final hybrid energy function, because obviously this picture here is a bit simplistic because we don't really in any way enforce that the neural network doesn't contain any pairwise terms. So even if we have an explicit pairwise term in our hybrid model, it might also be that the neural network contains some significant pairwise terms, and you also should take them into account when your task is really the reconstruction of couplings. And what you can do is to simply write down an expansion of the energy function and think about how you can actually extract the couplings from a generic energy. And the way you do that is that you take the energy. If you want to extract, for example, the couplings between positions I and j, you multiply by si and sj, so these variables here, and you sum over all sequences and you normalize. And this can also be then approximated at the end of training simply by doing a uniform sampling. And then, given these reconstructed couplings, we calculate the reconstruction error of the couplings, which is defined here. Here are some experimental results where we use only all 3 interactions. We use a multilayer perceptron with 1 hidden layer and 128 hidden units, and we vary the interaction strength parameter. So the higher order interactions become more dominant in the generating distribution from left to right here. And we have 2 different system sizes, and in these plots you see 2 things. First of all, if you use only a pairwise model, then the inference of the couplings becomes actually quite bad, simply because these higher order interactions confuse the pairwise model. While if you use hybrid models, and in this case it's really important if you use the explicit terms or the reconstructed terms, both of them perform much better. Even though, again, in the paper we do much more experiments, there are also cases where actually this reconstruction approach that I've just described is really important if you want to have a good performance, where the explicit pairwise interactions in the hybrid model don't perform that well. We can also go and check if the terms really match up. So if the neural network really extracts the higher order interactions in the generator, and the pairwise model in the hybrid model really models the pairwise part in the generator. And here we plot the respective energies against each other, and because these 2 lines are just very nicely diagonal, this is exactly what happens here in this specific settings. There are more experiments in the paper. And you can also then check really if the interactions that you see in the neural network, again by extracting them in a very similar way than what we've seen before, really match the interactions in the generator. And in this case, this is actually true. As for conclusions, we have shown that energy-based models are good candidates for knowledge integration. The models that we specifically discuss in the paper still are quite expensive in training and sensitive to hyperparameters, and we have seen some tendency to overfitting, so we will try different training techniques in the future. And currently we're working to port all of these ideas to proteins, and there are already some preliminary results in the paper. And with that, thank you for your attention.